Imagine an artist stacking transparent sheets on a light table. Each sheet holds just one piece of the picture, a sky, a tree, a character. Layer them together, and you see the whole scene. But pull one sheet and only that piece changes. The rest stays put. Docker builds images the same way, stacking one transparent layer on top of the next. Every instruction in a Dockerfile is like adding one new sheet to the stack. From lays the very first sheet, your base image. Run paints a sheet of installed software. Copy drops a sheet of your source files. The final image is the view straight down through the entire stack. Each sheet gets a unique fingerprint, a hash, based on exactly what is painted on it. Two sheets with identical contents get the same fingerprint. That's why Docker can share sheets between projects and reuse them from a local cache instead of repainting the same thing twice. When you rebuild, Docker checks each sheet's fingerprint from top to bottom. The moment it finds a sheet that has changed, it repaints from that sheet onward. Every sheet above the cache hit stays untouched. This is why the order of your instructions matters enormously. Put the expensive stuff you rarely change near the bottom, and the cheap stuff you change often near the top. Here is our Dockerfile. It is a tiny recipe for a Node.js web app image. We'll walk through it line by line, and watch how each instruction becomes a layer in the stack. The first line is a comment that tells Docker which version of the Dockerfile syntax to use. Comments don't create layers. They are just notes for humans. The parser version pin keeps your builds predictable. From Node, 20 Alpine lays down the very first layer, a base image. Alpine is a tiny Linux distribution, so this sheet is small. Every from instruction you write adds this base image's entire stack of layers underneath your own. Choose carefully, because it is the foundation of everything above. Workdir/app sets the working directory for any following instructions. It does not create a layer. It is just metadata that changes the meaning of subsequent paths. Think of it as moving your paintbrush to the right spot on the canvas. Copy package.json packagelock.json. / copies only the dependency manifests into the image. This creates a layer, but a small one. Why copy just these files first? Because we want them on a separate sheet from the rest of our source code. Watch what happens next. Run npm ci. Omit equals dev installs the dependencies listed in those lock files. This creates an expensive layer. It downloads and installs potentially hundreds of packages. Because this layer only depends on the lock files, it will stay cached as long as the lock files don't change. That is the whole point of putting the copy before this line. Copy copies the rest of your source code into the image. This layer changes every time you edit a file. But because it sits on top of the dependency layer, editing code never invalidates the expensive npm install below. That layer keeps its cache hit. Expose 3000 documents that the container listens on port 3000. Like wrkdir, this is metadata only, no new layer is created. It is a hint for users and for tools like Docker Compose, not a runtime command. Finally, cmd node server.js sets the default command. This is also metadata, no layer. Combined with the images layers above, it tells Docker how to run your app when a container starts. Notice the pattern. Small changeable stuff on top, big slow rarely changing stuff near the bottom. That ordering is the secret to fast Docker builds. Every line in a Dockerfile creates a layer, and Docker caches each one. But the moment an earlier layer changes, every layer stacked above it gets thrown away. That single rule decides whether your builds take seconds or minutes. Here is the villain. Copy ... then run npm ci. The first copy grabs your entire source tree, every .js file, every config, every lock file, and bakes it into a single layer. Edit one line of source code, and that layer's hash changes. Because npm ci sits above it, the dependency install gets nuked too. Now meet the hero. Copy package.json and packagelock.json first, and only those. This small layer changes rarely, so npm ci runs against a stable input, and gets cached as a fat, satisfied gold layer. Then, and only then, copy the rest of the source. Source edits now only invalidate this top copy layer. npm ci is safely below, untouched, reused from cache. You edit code, you rebuild code. That's it. Still, even good Docker files grow bloated over time. That's where Docker history comes in, the magnifying glass for your image. Run it against any image and it reveals every layer, its size, and exactly which Dockerfile instruction built it. Spot a 400 megabyte layer from run apt-get? You probably forgot apt-get clean. A giant layer right after copy ... You accidentally baked node_modules into the image. Docker history turns guesswork into a checklist. Bottom line. Put your volatile stuff last, your dependency manifests first, and let Docker history keep you honest. Cache wins, builds stay fast, and you ship more often. Every Docker image you build is a stack of reusable layers. and those layers live inside a local cache managed by the storage driver. Overlay 2 on most Linux systems. Think of the cache as a warehouse of pre-built bricks your builds reach for first. The cache speeds everything up, until commands like docker system prune or docker image prune, a sweep through with a broom, or disk pressure cleanup decides your layers are expendable. The deletion happens silently, no warning, no confirmation. The next time you rebuild, Docker finds its cache empty. Your build script dutifully pulls every base image from the registry and reruns every instruction from line 1. CI pipelines stretch from minutes to hours, offline builds fail outright, and network bills show up uninvited. First mitigation. Pin your base image by digest. Instead of from Ubuntu, latest, you write from Ubuntu at SHA-256, ABC 123. That hash forces Docker to verify the exact same content every build, so cache invalidation by tag churn becomes impossible. Second mitigation. Use multi-stage builds. Your heavyweight toolchain compiles in a builder stage, then only the slim runtime artifacts get copied into the final image, so even on a cold cache, what you have to rebuild stays small. Third mitigation. Know your driver before you trust the cache. Run docker info grep storage to confirm you're on overlay 2, fuse overlays, or whatever backend your host uses. A mismatched expectation is the root of half these cache mysteries. Cache eviction isn't a bug, it's an unavoidable trade-off between disk space and build speed. The professionals stop being surprised by it. They pin digests, keep final images lean, and verify their storage driver before every CI decision. Welcome to this Docker CLI inspection demonstration. We'll walk through commands that reveal your Docker installation's version, image inventory, layer history, storage driver, and container state, all from the terminal. Each scene shows the exact command, and its realistic output as you'd see on a Linux terminal. The clear command wipes the terminal screen for a fresh start. This is a standard practice before running diagnostic commands to keep output tidy and readable, especially when recording or sharing terminal sessions. The Docker version command reports the Docker client version installed on the system. It's the fastest way to verify Docker is installed and to confirm which version you're working with before running any other commands. The Docker images head-5 command lists the Docker images stored locally, piped through head-5 to limit the output to the first 5 rows. The columns show repository, tag, image ID, creation date, and size, giving you a quick snapshot of your image inventory. The Docker history Alpine, latest head-8 command displays the layer history of the Alpine image, showing each layer size and how it was created. This is invaluable for understanding what's inside an image, and identifying which layers consume the most space. The docker info grep storage command filters the full Docker system info output to show only the storage driver line. The storage driver determines how Docker manages image layers and container writable layers, critical for performance and compatibility. The Docker ps, a head-3 command lists all containers, both running and stopped, piped through head-3 to limit output. This gives you a quick view of container state, including container ID, image used, command, status, and port mappings.